morning, everyone. Thank you, oh ye few but faithful. Welcome, astrobiologists, to 8:30 in the morning on Friday. What are we doing to ourselves? No, I'm just kidding. Thank you so much for coming. My name is Brittany Schmidt. I'm an assistant professor at Georgia Tech. And I come to this community with a background in planetary science. And one of the things that I've kind of heard a lot, at least early on, was we'd start talking about the missions that were going, and at the time it was the Europa mission, the previous one, the one that never happened. It was called JEO, Jupiter Europa Orbiter. Missions change a lot, is what I've learned. But so before Clipper and what became Clipper, and the experience that I had, at least talking to astrobiologists, and in particular younger astrobiologists, was, oh, there's no astrobiology instruments on this. They don't really like it. Okay, well, maybe next time. And I was like, no, no, no. You have to come to all of the places where the decisions are being made, and we have to figure out how to get the instruments and the science that we're really interested in on the missions, right? So we've been talking, we've now spent 5 or 6 or 7 days, depending on when you actually arrived in Mesa, talking about astrobiology and the significance and how to discover life in the universe. But we still have n equals 1, right? We have one example of that. And in order to do that, we're going to probably need spacecraft missions. And so the purpose of today's panel is actually to just kind of talk about the process of getting instruments and getting missions going, and how to try to influence or try to improve the amount of direct astrobiology instruments, and very importantly, how to have this conversation and how to improve the number of instruments that are doing specifically our science. And I think one of the really important things we have to think about is that we can't be frustrated with the missions of today if we didn't do the technology beforehand. And that's a very long path to development. And so these are just kind of supposed to be informative for people who haven't been on missions before, be perhaps hopefully a way to solve some problems for those who are currently trying to get missions through the TRL process, technology readiness level process, things like that. So what we're going to do is we're going to have a quick introduction of the panel. Mary Wojtek's prepared a couple of slides about the interest behind it and the motivation behind astrobiology on missions. And then each of the panelists up here has some kind of experience getting instruments and science on missions. They'll talk a little bit about their experiences, and then we'll kind of open it up to a discussion about how we might change that, or how we might be better informed about how this process works and how we might improve it for the astrobiology community in the future. The first thing that I really wanted to mention, though, whilst I have the podium, is that one of the things that's very, very important in the current organization of NASA's scientific community is assessment groups. How many people here have been to an assessment group meeting or know what I'm talking about? That's what I thought. So assessment groups, Mars exploration, so MEPAG, OPAG, the Outer Planets Assessment Group, SBAG, unfortunately, what a terrible, terrible name that one is, but the Small Bodies Assessment Group. These are actually how the community gets together and does some of the, I wouldn't say politics, but does some of the organization that's not exactly science. And that's where these decisions are made. So MEPAG, for example, is where most of the landing site discussions are held for Mars 2020. So if you haven't been there, or you haven't participated in that, you haven't given them ideas on where they should land and look for things that we care about. So getting to MEPAG and getting to OPAG, I'm in the Outer Planets community, getting to those places is really, really important. We had a roadmap for Ocean World meeting on Monday, and my experience so far has been that mostly those were planetary scientists, because we email out to the planetary science community, and the information doesn't always make it out to astrobiologists. So if I could give you one piece of advice, it is that the assessment groups matter. They don't have science necessarily at those meetings, but you should really think about it, because that's where you actually impact the direction of future, at least directed missions. And it's a great place to go for information and to just figure out how it works. So anyway, so now I will get down off of my high horse and introduce our panel. Mary will get on it soon thereafter. So let me quickly introduce everyone. This is Dr. Mary Wojtek of NASA headquarters. If you don't know her, you should probably come up, hug her. She does a fantastic job. She's probably why myself and many other people in the room have dollars and also have a career, and thank you very much for everything that you do. Next to her is Stephanie Getty. Next to her is Erin Noel. Next to him is Amanda Stockton. And next to her is Dr. Jim Bell. So actually, Dr. Zoll, I apologize. So everyone is a doctor, as it turns out. All right, very good. Let's go ahead and, Mary, would you inspire us with your information?
All of us are doctors, but no one will help you if you're sick. So, okay, so I'm going to start out with what leads us to this incredibly important time in astrobiology and at NASA, and start with this great picture we took the other day. Astrobiologists, 800 strong and growing. This is the largest meeting we've had. The last one, there were about 750 people registered. Yay. And what's incredible, of course, and one of the reasons we decided to take the picture, is if you look at the demographics of this shot. Basically, we worry about the future workforce. I think the future workforce in astrobiology is incredibly safe. We need to keep making sure that it's strong, but we're ready for what's coming. I'm going to start out by giving you sort of two perspectives to assure you that the public is extremely interested in what it is that we do. So the top figure is a graph since January 1st of 2015 of announcements that were made at NASA and the page views for each of them. And so, of course, people continue to be fascinated by Mars. They continue to be fascinated, or not continue, but they're getting more and more fascinated by, you can see down there, want to move forward, lean forward. So you can see that that's one of the highest ones. There's also interest in exoplanets. Turns out that TRAPPIST won the announcement there in many regards, surpassed almost any other announcement that we had. But below that is another image just showing their own social post and the reach of those. And so again, we see Mars water being important. We see Europa's water plumes being important, exoplanets and TRAPPIST. So, and I just want to share with you, I was part of the, whoops, actually, let me go back a second. It's not plotted on here, but I've been told that the recent announcements of hydrogen coming found in the plume of Enceladus and a confirmation or second observation of plumes from Europa was about a quarter the size of the TRAPPIST. And what they considered in NASA promotion or PAO speak, you know, a top story of a year, maybe not of all times, but of a year. So again, we continue the interest with the public. I want to share some of the things that came out of that press conference, which I was part of. Some of the reactions, one of my favorite, so they had a bingo on social media, and one of my favorite was someone designing their own graphic of what was going on in Europa. And one of the quotes that came out of a microbiologist that was actually working on it was that Europa was producing about 35 pizzas a day as food for microbes. And again, they kind of got the chemistry wrong here. They decided to make pizza. They equated cheese and sauce and toppings with carbon and hydrogen because they thought they were making methane. But you see the point. They're actually getting it and responding quite positively to us. The other thing, of course, is another favorite is on the left. People are a little disappointed that there aren't whales or porpoises leaping out of the plumes of Enceladus. And someone is all ready to go and give a perspective of what maybe it might be like to be within one of those moons. And here are some of the, the comments that were, I thought were quite fun. Who wants to come ice fishing on Enceladus? And again, NASA has delivered amazing news. One of Saturn's moon, Enceladus, could harbor life in its ocean. And then I just want to note that one of the reasons that we predicted that perhaps we didn't get as much coverage as we thought we might is the fact that at the same time this was going on, we had dropped the mother of all bombs, and so there was some competition in coverage and interest in the public. But I really like the observation on the right, which is, so we dropped the biggest non-nuclear bomb ever. NASA's is already looking for ways to get out of the planet. Take me with you. So So in addition to the public, their representatives in Congress are extraordinarily supportive of astrobiology and the search for life. That while we were attending this meeting, there was a hearing at Congress in the Committee for Science, Space, and Technology, and this is from the statement that the chairman, Lamar Smith, made about the hearing on advances in the search for life. You know, he acknowledges that we have pioneered, and it's not the United States, it's us in this room, and you know, everyone who's attended this conference and beyond have pioneered the field of astrobiology and continues to lead the world in this type of research. Since its beginning, NASA has searched for life beyond Earth. And then he actually has a call out or a shout out for us. He actually acknowledged that part of the reason that while he was discussing advances and considering or educating the rest of Congress about astrobiology, we were here doing our jobs, sharing with each other our new research findings and working together to plan for future opportunities. And then I want to hit on a little bit with something which is extraordinarily exciting to me, and that's the NASA Transition Authorization Act of 2017. In coming to NASA headquarters, I got to relearn civics. I didn't really understand how bills were made and budgets get signed and all that stuff. So the authorization is actually setting priorities for agencies, and it's an opportunity to give direction that signifies interest by Congress. It also is an opportunity to change the existing enactment laws that govern agencies and other activities within the federal government. We haven't had one since 2010. For NASA, but we had one signed this year, and there's some really important legislative or directives and legislative changes in this. The first is, again, signaling how important searching for life is. It's targeted all of the areas that we're interested in terms of moving forward. When Congress asks us to ask the National Academy to look at something, that means they're really interested. So Section 508 asks the National Academies to do a study to understand how to study and explore extrasolar planets, and in the language, it very specifically links it to looking at habitability and searching for life. 510 talks about expanding public-private partnerships, there's a tremendous amount of philanthropic interest in supporting us, as well as foundations that want to fund the science, as well as the technology. Section 509 requests that we go and get a strategy for searching for life. Right? And then the final one is, again, continued support for our Mars program. What's the architecture now? We've got 2020 in the pipeline. What's going to happen after that? We want to hear from the broader science community, or they want to hear from it. And the thing that I think is most amazing, and I'm going to end with this, and I want a round of cheers and applause, is within the Space Act, there's the first part of it outlines what exactly NASA is supposed to do. And there's a section called Policy and Purpose. And since this year, there have been 9 of them. And I want you to look at number 10. We are in the top 10. We're number 10. The search for life's origin, evolution, distribution, and future in the universe. That is us. Astrobiology made... So all I can say is we have public support. We have their representative in Congress that, somewhat control the purse strings, so we've got support there. We've got a fantastic workforce ready to do the job. We need to grab this, ride this tide, and expect incredible opportunities and an amazing future, but we all need to be part of it. So I think this is going to be I'll only iterate that my version of what one of the things that Brittany said was, if we only have hammers in our toolbox, we look for nails. We need to work with the community to develop new sets of tools to draw stronger, provide stronger advice about what the measurements are that should be made, so we can get those tool designers to make those tools, so that we're not just looking for nails across the universe. Thank you. Dropped my earring. I do this all the time.
All right, perfect. So, Stephanie, would you like to take it away?
Sure. Is this live? Not yet. Oh, yes. Hello. So as Brittany mentioned, my name is Stephanie Getty. I am at NASA Goddard Space Flight Center. Brittany kind of gave us some guidance on what we ought to cover for our introductions. And so in kind of this science realm, I'm interested in how organics are distributed throughout our solar system and really what constitutes the best way to differentiate between an abiotic signature and something that derives from biology. And I do that through really instrument development and instrument science in the sense of looking at the best possible terrestrial analogs that we have for a variety of environments that may be of interest to this community throughout the solar system, including Mars and ocean worlds analogs. And then a large component of what I do is in really the instrument science and how you make the best measurements to get at those answers. So in terms of my involvement in flight instruments, I'm on the MoMA science team and part of the MoMA mass spectrometer development team at Goddard. That's one component of a German-led instrument, MoMA, that will go to Mars in 2020 and rove around and then get at the deep subsurface. Deep is a relative term here, 2 meters down. And so thinking about drawing parallels or conclusions from what Mars Science Laboratory has measured and some of the predecessor missions will have measured, and how do we extrapolate to do now the science that needs to be done to inform our expectations and our data interpretation when we do get there with MoMA. So that's an example of an instrument that has really not flown before. The mass spectrometer is a new type of mass spectrometer that has not flown before, and it has some new capabilities. So if you're looking for pushing the envelope on the science questions that you want to ask, sometimes you really need to go after new things that really match the requirements that you're going after. And so MoMA is a good example. It's a very sensitive mass spectrometer, and it overlaps with some of the capabilities that we have flown previously in its gas chromatography, but it also uses laser desorption ionization to look at unprepared samples for high molecular weight organics, which is interesting. Now, as an instrument that hasn't flown before, it's been an educational experience, particularly for me, coming from more of a lower TRL instrument development career to this point, and then watching what it really means to get something new developed and matured and ready for flight. And it's been an incredible experience, an incredible effort by a really talented team at Goddard, which is exciting. Do you want me to stop there, or do you want me to answer your third question?
Yeah. Go for it.
Okay, so I had trouble with your third question a little bit, but the third question was describe a recent challenge in getting something with astrobiology capabilities flown, and I think rather than answer that directly, what I will say is, I was trying to think from NASA's point of view, from headquarters' point of view, what it means to develop a portfolio of instrumentation. And I think the possibilities for making measurements that can really get at very important science questions, particularly in the search for life, requires a lot of parallel efforts and really a broad portfolio. And so from headquarters' point of view, I don't know, but I presume that it's useful to have a number of possibilities at the ready when you are trying to put together your next mission. From an instrument developer's point of view, there are never enough missions to get everything flown. So there's an inherent tension there. But I would say that there are a lot of instrument capabilities that are in development and really at the conception phase right now, even that would be very deserving of finding their way onto a mission, and hopefully we can continue to work as good citizens to try to increase the number of missions that we can get out there so that we can make those measurements.
I'm Erin Noel, and I work at JPL. And so my background is as a physical and analytical chemist. And so I guess I, like everyone, as we were discussing, work on many things. But one of my real interests in astrobiology and instrumentation is on really doing sort of contextual habitability measurements, and specifically through sort of measurements involving soluble ions. So I've put a lot of time into trying to develop microfluidic instruments that can separate and detect a variety of markers related to habitability, and so trying to miniaturize techniques like capillary electrophoresis or ion chromatography, and so doing also a lot of work at low TRL. I guess my mission experience is pretty limited. It's in the proposal process. So, but working on that has showed me a lot about what you need to do to try to take things all the way and really propose them as credible instruments and have it be a strong part of the science case. And my experience in that is with sort of the wet chemistry lab team and the heritage of that instrument, which was an array of electrochemical sensors designed to search for soluble ions. And so we're continuing to try to develop those tools for Discovery and now New Frontiers proposals. So I guess, and challenges, well, there are always a lot of challenges, but I think in a way Brittany hit on one of the biggest, which is, I think it comes down to perseverance. I don't know if any of you were at the IPM meeting a few months ago, but both Chris Webster from the tunable laser spectrometer and Luther Beagle of Sherlock gave really great talks about sort of what it takes to go through the process of developing an instrument and getting all the way to the end, the end goal of being included on a mission, and in the case of TLS, delivering, incredible results. So, it's basically a nonlinear story of keeping at it, and I think I haven't solved it yet, but that's I think it's a good model. So.
Right. Hello. Is this on? Yeah, excellent. I'm Amanda Stockton. I'm an assistant professor at the Georgia Institute of Technology. I've been there for about 2.5 years now, and my interests are pretty much all of the questions of astrobiology. Is there life beyond? What are the limits of life on Earth? How does life begin and evolve? And my group tries to tackle all of these questions in a number of different ways, but we use microfluidics as our core technology for all of these things. And I think microfluidics has a lot of strengths for space flight because it allows you to do some of these wet chemical analyses that are otherwise rather challenging to do down at the small scale. My experience working on missions began whenever I was a graduate student with Rich Matthews at the University of California, Berkeley, working on the microchip capillary electrophoresis system with laser-induced fluorescence detection as part of the URI instrument package on board the ExoMars rover. It's a lot of words to say, but I was kind of forced into early graduation when the instrument was de-scoped from the ExoMars rover. At that point, I went down to JPL and worked with Peter Willis as a postdoc and kind of helped get that program up, and it has been incredibly successful since then. So I like microchip capillary electrophoresis with laser-induced fluorescence detection for a number of reasons. LIF is incredibly sensitive. You can't hardly beat it as a concentration-sensitive method. We're looking at the capability to detect 70 picomolar of an amino acid from a sample plug as it passes the detector that's 35 microns by 35 microns by 100 microns. That's attomoles of sample. And I like microchip capillary electrophoresis because you just can't beat the resolution, and you can get chiral separations as well. So that's one of the technologies I continue to work on and have been involved in various instrument proposals, including to Mars 2020 with the Mars Organic Analyzer out of UC Berkeley, PI'd by Rich Matthews. And we continue to attempt to get this type of technology on a mission because we just believe that it is so powerful. Currently, in my group, however, we're focusing on the low TRL development of various instruments, still focusing on microfluidics and laser-induced fluorescence detection, and continuing a little bit of microchip CE as well. So one of our projects has no separations, but it is capable of withstanding a hard landing with an icy moon, slowing down from approximately 5 kilometers per second and a 50 millisecond pulse. That's 50,000 Gs. That's our design limit. We've tested up to 12,000 Gs so far, but hopefully we'll be able to get the rest of the way there. And also have a little bit of work developing microchip CE with mass spectrometry detection so that we can not have to do derivatization in order to detect and chirally resolve amino acids. So I think one of the big challenges that we're looking at here was hit on by Mary Wojtek here, where if we only have hammers, we're looking for nails. And Stephanie said we don't have enough missions as instrument developers. And so I think this hits on something where heritage is such a primary selector in what instrument gets selected for a mission. And not all heritage is equal. There's a difference between an instrument that performs beautifully, gives you the data that you're looking for quite easily, and one where the data comes back and it's messy and confusing and challenging to figure out. And so perhaps we could have more missions and be able to select some of these instruments that are very, very promising but don't yet have the heritage.
Okay, is this on? Good morning. Hey, I'm Jim Bell. I'm a professor here at ASU in School of Earth and Space Exploration, and I work with the spectacular Brittany Schmidt on the board of the Planetary Society, big friend of astrobiology. Mary called me the old man on the panel, so I guess I'll take that role. But you're the old lady, I guess. So.
I said we were the
So I'm not a real astrobiologist, but I play one at work. I'm a camera guy for the most part. I've been involved in imaging investigations, Mars imaging investigations from Pathfinder and Spirit Opportunity, Curiosity, and I'm the PI of the Mastcam-Z cameras on 2020. So think a lot about cameras. And as an imaging person and primarily a geologist, a little bit of a mineralogist, I think about the ways that we can do astrobiology with those kinds of imaging systems. Of course, we could take pictures of things walking around on the surface. That would be spectacular. But more realistically, what we do astrobiologically with the imaging is try to understand the context and the history, and what was this environment like? What were the conditions like that could have enabled astrobiology? So in that sense, it's a simple instrument. In the sense of not having to, invoke all the complexity of many of the things that I didn't understand half of what you were saying, but it sounds really complex. And that's a theme, and heritage is a real theme to come back to. I wanted to touch on a couple of recommendations or ideas to pass along. Brittany, I completely agree with you. The ags are sort of where it's at for getting input into the machine that cranks out mission requirements. There's, you mentioned MEPAG and SBAG and OPAG. Why isn't there an AbSag, right? I mean, whatever we call it, right? But, this community is getting to the critical mass of where, some advocacy with the right people would maybe push that over the limit. And so instead of having to be piecemeal in these other groups, maybe this community could have its voice heard uniformly. That's a community kind of thing. As individuals, what I try to tell my own students and other young career professionals is get yourself on a science definition team, get yourself on an NRC report like the ones that Mary previewed. They're coming up, right? Get yourself on review panels. I mean, people can volunteer for review panels. How often does that happen? You guys are giddy when they do, right?
Absolutely.
Yeah.
Actually, people volunteer. But they don't come.
Yeah. Okay.
You need to show up.
But the point is to become part of the process, and what comes out of assessment group white papers and consensus reports, what comes out of science definition team reports folds right into what the mission will need. And so, if you are a strong advocate and believer of methodology X and think that that is going to make a huge difference, get your voice heard, pull your friends and colleagues together, point to your papers and abstracts and presentations, and try to convince groups like that, hey, this is really important. And of course, you never know what comes out of the other side in these sausage-making exercises, but sometimes what comes out of the other side is a requirement for a mission investigation, and you say, oh, I do that, or I can do that. So that's a way to get into it. The topic of heritage came up. I think the simplest way, and I've had both kinds of experience. I've written plenty of proposals that have gotten rejected, and I've written some proposals that have gotten accepted, and it seems like, in my case, the common theme of the ones that have been accepted are the ones that had the highest heritage. It's sort of natural human nature, conservative review panels. They're looking for incremental advances, not leaps, because leaps are risky. And you can take that risk. It's okay to take that risk, but just know that you're going to be competing with others who aren't. And so when the review panel was kind of biting their nails and saying, ooh, how do we really guarantee success here? Or do our part in guaranteeing success? They're looking for lowest risk. They're often looking for highest heritage. So, but that's not a killer, right? You can take your novel idea, and I think it's possible to sort of incrementally tack novel ideas into high heritage instrumental solutions. I think what Stephanie talked about with the MoMA instrument building on things that have been done for SAM or others, I think that's a great example. Sneak in a capability, maybe not sneak in, but get in a capability that is not going to scare away reviewers or headquarters in terms of risk, but it's doing something new and different. Some aspects of Sherlock, which was mentioned up here on 2020, same kind of thing. Using some high heritage components for imaging, et cetera, but getting in this UV capability that a lot of astrobiology people want. So think about not hitting the review panel or NASA over the head with a 2x4 and saying, you guys you gotta pick this. This is the way. But instead, use little toothpicks and kind of poke at it, right? Bites of 1,000 ducks, right? And then, so find those increments. Support from a center or your institution or your university, absolutely critical. If you can partner with a Goddard, with a JPL, with an APL, with a SWIRI, or here at ASU, we get an enormous amount of support from our own administration for proposal writing and for facilities that can support instruments that people like Phil Christensen, Mark Robinson, myself, and others have put together. So go to bat for yourself with your own institution or make a connection to a center. And then I guess the last little piece of advice thing, and maybe I know a lot of especially young people don't realize this, but if you really want to head down this path, you're probably going to have to put your science career on hold. And that can be challenging. If you're trying to get tenure, or and the rest of the people in your department or your group are like, where are your great science papers? And it's like, oh, I'm working on this instrument, and they may not understand, So it's sort of common in the engineering world or the astronomical instrument world that you sort of, people in your world understand you're building this thing to do great science. But make sure your own community, your own institution, university, center, or whatever, understands that as well. And then my own challenge is just ignoring all of my own advice. So I mean, you get enamored of some cool idea, some interesting new detector, some new riff on a way to do an imaging or a spectroscopy investigation. And I got to write that proposal. And in the back of my mind, it's like, man, they're not going to pick this. But you can't stop. So part of that is just write the proposal. Write the proposal, get the feedback, go through the process, and then persevere.
Thanks. Yeah, so hopefully this is kind of a range of perspectives from aspiring from policy and everything. My own experience is that I'm on the instrument team for the ice-penetrating radar on Europa Clipper. I'm not a radar person. It's really funny because we tend to, I think, as planetary science, be like, oh, you are a camera person, and you are a spectrometer person, and I apparently am a radar person, which is hilarious because I've never actually worked on the data from such a thing. So, but I think that's the other way to think about it, is that there's opportunities to figure out what's out there and how you can make it an instrument that you could use. And that's another tack you might take in the short term before the instrument development processes. So I got interested in ice penetrating radar because I really wanted to understand how the ice shell worked on Europa, because I wanted to figure out how long it took for biomarkers or something like that to end up at the surface, or really what's the context for that thing so that we can interpret it appropriately. And that's a journey that started a long time ago. And so when I finished my, as a grad student, I heard that the then 2007, the Jupiter Europa mission and Jupiter Europa orbiter was starting up the study, and I told Bob Papalardo, I was like, I will shine shoes, make coffee, do anything. And luckily I put also take notes in this list of things that I would be willing to do in order to help with that mission study as a person who was too early to have applied to be on the science definition team. And so Bob was like, oh, we don't have anyone taking notes who has actually done science before, so that sounds like a great idea. And so in 2007, I also had a thesis advisor, even though I wasn't working on Europa, that would pay for me, because I really couldn't afford to drive from Santa Monica to LA, or to Pasadena all the time, 4 days a week for 5 meetings a year or 6 meetings a year. And so he was like very supportive of this activity. And so he was like, of course, we'll cover your gas mileage, gas mileage back and forth. So I was like, great, this is fantastic. And all I did was take notes. But one of the things that I got very, very fast at was being able to write something down, think about it, and then discuss it. And it was a really great environment to do that. And so then it also allowed me to talk to people who were in the room and listen to the science cases from people who had been, elected to this position by NASA headquarters. And what it gave me an opportunity to do was say, I want to work on that instrument with that person. I made a list of 5 people, and then I just made a really hard case at the first one, and luckily they said yes. But when I decided I was going to go to Texas and work on ice-penetrating radar, as a person who had just done their PhD on Hubble observations of an asteroid, people were like, why would you do that? You're the asteroid person. That seems crazy. And then it was a little crazy, but it also worked out really well. And so I went and I started working with folks that were building radars and flying them around in Antarctica, which is not exactly what I'm doing now. I'm building other types of instruments that go to Antarctica, but I wouldn't have gotten a chance to do that if I hadn't done that. I hadn't been in the room and been watching how people were discussing their science and what they wanted to do. And then just tried really hard to convince someone that I could turn a radar or help turn a radar into an astrobiology instrument. And so that was a really fun and different way of looking at a career path. And so then that's the same way it was getting involved in being a faculty member. Was I need some space to think about these ideas myself. So there's a lot of different, I think, experience up here, but that's why I wanted to kind of highlight the ways that you might think about getting involved in missions so that we can make this life detection thing. So anyway, so I wanted to start off, and then we've got about half an hour, 20 minutes or so, and to just kind of have a conversation. So if folks have questions, please come up to the mic, and I'll just kind of get us started. So anyhow, so what I wanted to know actually was, so we talked a little bit about heritage and TRL and things like that. How do we, for some of these instruments that might be possible, a new type of mass spectrometer, there's a lot of heritage parts, a new type of camera with another filter system or something you could imagine being astrobiologically relevant. But how do you get around the fact that, for instance, microfluidics devices haven't really been flown? How do we get to that point? So I was just wondering if someone would like to take the point on how do we get those things that don't have heritage and don't have a pathway, how do we create a pathway for that to happen?
Well, I guess I can speak to that sort of in the sense that that's not entirely true. I think that's a misconception, and I'm going to promote a colleague, Tony Rico's work out of NASA Ames, where they've been among the first to do some amazing small sat payloads using microfluidics to do biology experiments. So in fact, and so that's a great template. There are a lot of sort of nooks and crannies to try to put things into space, and as soon as you're in space, you have heritage. And it may not be perfect heritage, but then you're sort of maybe closer to I take a piece of this and a piece of that, and you can start to build it up. So I guess for microfluidics, I think it's slow, but it is actually happening, and that's taking those opportunities and putting them together is what we need to keep doing.
Mm-hmm.
Yeah, go ahead.
I was just going to add on, you were talking about the small sats, but there are a number of other flight opportunities that you can take advantage of through the NASA proposal system.
Yeah, I would just say fly it anywhere. Balloons, high altitude aircraft, small sats, CubeSats, sounding rockets, and also try to take advantage of the technology development programs. They're crazy competitive. But you got to write the proposals and realize maybe it's going to take you 2-3 times. You're going to get feedback from the review panel. The proposal's going to get better. But that is a path to move it up. But I guess I do kind of agree, though. There's this wall that you're trying to jump over. And once in a while, you do see just a really new thing appear on a mission. And for whatever reason, it's the time is right for that measurement. The risk posture is lower. The review panelists all went out and got drunk the night before. Whatever, and so I think it also comes back to perseverance.
With those new technologies, do they tend to have widespread adoption in the scientific community ahead of time?
Well, I mean, some are coming from, some are kind of a manifestation of the fact that the scientific community is working with the commercial world, and these things are becoming benchtop, desktop devices. They're just becoming more reliable. The perception of the risk of some of these methodologies goes down as they're more widely adopted in the community and in the commercial world as well.
So can I speak to the entry level? So Jim mentioned the various calls that we have, and very recently we reorganized our technology development to separate and refocus some attention on early ideas and what they call TRL level 1 through 3, and then things that actually start getting developed to get closer to flight. And I think that for many in the room, you're not worried about flying something, you're probably worried about that entry level. And so if you have an idea, you should look at the sorts of calls so we think we're clever at headquarters, we like acronyms, and one of them is Picasso, and that's the entry level one. And the one that's more towards maturation is Matisse, and that's no comment on the talents of those artists. And so I think that the entry level for this group is for many of you, is Picasso. And perhaps if you don't have an idea, Jim also mentioned, if someone tags you to review, we do get people who review on our technology that also, technology panels that also are focused on the science, on our evaluating how important is this method, starting to give feedback to proposers about what kind of handling, what kind of limitations you've experienced yourself, even when you're in the laboratory or in the field using instruments as they're proposing. So I think for this group, getting involved at that level. And then I will just reiterate that they've identified, we know that we first realized as a part there was something called, I guess the Valley of Death is used for lots of things, but there was a Valley of Death for technology in the jump from one to 4 maybe, and then to get 5 and 6 and ready for flight. And so we've shifted for that. We also know there's this problem with getting access and developing heritage. And as these guys mentioned, there are balloons, there's the ISS, there's small sats, there's a bunch of different programs that are likely to, because they're relatively inexpensive, to provide opportunities for flight.
Let me also offer the piece of advice to really get to know the heritage instruments, because when you know what the heritage instruments can do, then you can use your thinking self to actually understand where the gaps are and what naturally falls out of the science requirements and maybe meets the science requirements best. And so I really like what Jim said about maybe taking a hybrid approach where you let the heritage instrument do what it does best, but take a look at maybe the science that is really best done by something that might be a little bit new.
Yeah, I've got a great example of that too, as actually the ice-penetrating radar system that we're now sending to Europa was actually first proposed for Europa, but was really difficult. We didn't get any missions, and what ended up being the first ice-penetrating radar was actually an ionospheric sounder. And so they were like, this could be used as an ice-penetrating radar, but we're sending this as an ionospheric sounding instrument. It's called MARSIS, and so it's relatively low resolution, but what it's turned out to do is absolutely spectacular subsurface sounding in icy areas. And so it's a perfect example of being like, this is an ice-penetrating radar. Wait, no, it's an ionospheric sounder. And so it sounded like a thing that people had sent before, and it was, because those technologies are similar. So anyway, so I think that there's lots of pathways. I know there was at least one question, yeah.
Well, just building a little bit on the entry, I would be remiss representing NIAC if I didn't point out there's another path for entry into trying to understand whether your instrument is ready for prime time. Mary talked about the TRL level 1, 2, the Picasso-Matisse pathway. If you're TRL 0, then NIAC is the right place to try to suggest that maybe you have a concept that isn't ready for prime time but should be. And Penny Boston is a fellow of NIAC. Lynn Rothschild's a fellow of NIAC. So we have astrobiology types that are well represented in our cast of fellows. But the real difference in NIAC from a technology development program is we really don't pay you to develop your technology. What we do is we give you a grant of about $125K for a year to show us that your technology should be considered for NASA by putting it in a mission context. And if you are interested in this at all, it's highly recommended that you talk to one of us in the program office before you submit your bid, because the hard part for communities like this is taking their technology, which is what they really love, the instrument that they really love, and putting it in a mission context to show that it's something that NASA would want to do someday. So, this is for all of you dreamers out there, both the entry-level postdoc graduate students and all the way up through the seasoned guys that have had this thing banging at the back of their head for decades, but they just didn't know what to do with it. So we fund about 15 to 16 grants a year at the phase 1. Something to consider, and we in the program office are happy to help you understand what the constraints of the program are, since it is different from a formal technology development program.
Thanks. Are there anyone else with nobody has questions for how to get an instrument on a spacecraft? Come on, man. All right, Zach.
This might be kind of a wide-ranging question, and I welcome responses from anyone about this, but it seems as though on the launch services side and the commercial side, there's a changing relationship of risk with launch vehicles itself. And I wondered if there's any sense that the TRL development program itself might have to anticipate and evolve with the increased amount of risk that a lot of these launch service providers seem to be accepting for themselves. Blue Origin and SpaceX, for example, and in the satellite development and the rapid testing, rapid prototyping, rapid flying kind of regime that they're entering. Is there an anticipation that the TRL development program will evolve to be more like this, or on the other side, that there might be some dialogue for mirroring the TRL development program with some of these private people and try to find some areas of overlap?
So that's a great question, and you're right. The commercial world is really starting to come online with opportunities for science, which is spectacular. But personal experience, I don't see them thinking that way. I don't think they think like NASA. You want to launch a small sat with a crazy, risky experiment that you're not sure it'll work, and it's got some moving parts. Will it survive the shock of launch? Will it work in the right environment? But boy, if it does, then it's got that heritage, and you can make the case to get it on. A SpaceX or another launch company, they don't care. Are you paying for the ride? You buying the ride? Okay, go. Have a good time. And so it comes down to having to talk Mary into paying for your launch, or your university president, or your center director, or you're independently wealthy and you just pay it out of pocket. But that's incredible that you could do that. Any of us could do that. Now, that's totally new. What's happening, I think, is there's going to be there's already this developing relationship between NASA and other space agencies with the commercial sector, and buying launch opportunities. And then it won't be a free-for-all. There'll be a competition, but NASA's providing these opportunities, and then you're back to competing and trying to make the case that this deserves a shot at this. But it is the case that you could just do it on your own nowadays, which is kind of cool.
Yeah, question.
So this might be, I guess, a no-brainer, but I sometimes get the impression that we as astrobiologists get a bit tunnel vision upwards, and that I guess comments from you about, there's science still to do here on Earth, and I'm sure the people who were in the hydrothermal vent sessions here at the conference would love better mass specs and better electrophoresis devices to put on subs, and I know for certain I would love better instruments that I can put under harsh conditions in the lab. So there's collaborations there with colleagues who maybe you might not otherwise work with, and things to do there. So maybe you have comments on that.
Yeah, actually, so Amanda and I are doing exactly that. I was a crazy person, decided to build a robot with my startup, having not done that myself before. But what's awesome is that since Amanda's at the same institution, we threw a microfluidic device onto our proposal for that. And so we're actually trying to do that, like little pseudo missions. And it's a great experience too, because leading technology teams, even as a scientist with a scientific background, is a really great place to cut your teeth on figuring out how a mission might work on a greater scale. So Amanda and I have an example of that kind of thing. And I think that's very true, is that there's ways to pitch the instruments back and forth and get them more experience. But Amanda, maybe you have a couple more comments.
So, as you know, Adam, a large fraction of my program does do field work. And so there's a lot of science that you really would love to do in the field, and some of these new technologies could possibly help you get those done. And it's great for the instrument developers too, because basically you need to be able to show that it would work here before you have any hope of it working elsewhere, in my personal opinion, and I think a few of you may share that opinion. So partnerships between instrument developers and field scientists is a wonderful route forward.
So I'd say that NASA's focus to a great extent is, yes, we look to the stars and beyond Earth, but we know that we're only going to get there if we understand how to do things here on Earth initially. And I'd just like to share a success story that is a prime example of iteration of development between funding from NASA, funding from NSF, and funding and development at WHOI. And that was, we funded a group to develop, to further develop a mass spec, to develop autonomous operations of a vehicle. And this group at Woods Hole, led by Dana Yerger, then actually was asked to deploy this to map out the Deep Horizon plume. And the underwater vehicle had been developed by WHOI through independent other funding, but that autonomy and that instrument were instrumental in actually being able to determine what was happening with that plume. So those are things that we look for. We really know that we have to partner, and we know that there is a gigantic source of talent and engineering capabilities and instrument development going on for exploring our own world.
And you really don't want to reinvent the wheel, right?
Yeah.
And so Goddard hasn't lost sight of this either, and we have a very vigorous field work aspect to our work, and also partner with people who go out to the field and get us interesting samples that we can exercise our instruments with. And there's a new Picasso, in fact, at looking at underwater mass spectrometry. So definitely of interest. Yeah.
Yeah, I just want to make a comment. I think this is a very good discussion on, how to make use of what we can do here so that your instrument looks like it's more ready for spaceflight. The equation is not necessarily heritage and risk, but it's actually cost risk. And so much of the review is, well, this looks like a really interesting instrument, but it hasn't been flown before. We don't know if it can get there. And it's not whether or not the instrument will work. It's how much money is it going to cost NASA to get it to work, to get it on the launch pad. And so doing things such as getting on CubeSats or getting into the field and having your instrument do things in different environments helps reassure the review panel that even though this may not have flown, it looks fairly robust and it's not going to be a big surprise expense to get it to the launch pad. So that's something to keep in mind. And so the other half of that equation is, if you have a cheap instrument, you'll probably have more opportunities because they'll be willing to take that risk because it's not that big of an investment. So, and that kind of plays also into the commercial thing where Mary may not want to cough up the money for a launch and $100 million for an instrument if there's some concern about whether or not the launch will be successful.
Sure.
But if it's a relatively cheap flight instrument, you might be willing to make that bet because the payoffs are worth the risk.
Yep.
I would also say just something to think about is figuring out how to be one of those people that's reviewing. So there's kind of a bank of experience, and they'll pull from that to review missions the same as for instrument proposals. But I'm gonna mess up the name. The TMC.
TIMCO.
Yeah, TIMCO. So the TMC panels. So that's the technical evaluation. So there's a science evaluation of missions and instruments, and there's a technical evaluation. And so those are kind of separate processes. So if you have interest in this or experience in astrobiology, I think we need more astrobiologists reviewing for those things. So I would say, talk to headquarters about how to do that, because having people that understand the science and the technology that are new and very important to this community on the review panels, I think will really also very much help.
That's a great point. I'll just add one thing. So technical, management, cost, other. I think they've dropped the other, but
yeah.
So Brittany's right. There's two separate review panels essentially that review these things, and I will say from experience, your instrument, your idea, your mission could be technically spectacular, amazing management, right on the line on cost. If you haven't excited the engineers and the managers and the cost modelers with the science, you're not going to get selected. So the science really, it's really heartwarming to me how it drives that technical side of it. You want your engineering buddies to be, oh my, we have to do this. This is spectacular. Now let's pick it apart.
I was going to say one good entry too. In fact, it was the very first interaction I had with NASA. I was on an A-STEP panel when Michael Meyer was running it. And it was amazing to interact with engineers. I actually had a little book that I kept creating my own lexicon of exactly, so I would understand what brass board, breadboard, and all sorts of other things meant. But it was really fun trying to convince them of my excitement for a scientific purpose for an instrument or technology, and them to laugh at me at my naivete. But after that, I mean, again, P-STAR is now the current A-STEP. That's a great way. You get a nice mix. You can feel relatively confident that you have something to offer because there's science in that, but also get a really great introduction to technology and mission operations.
Yeah.
Yeah, that's a comment on getting to the high TRL levels is that even a sounding rocket or a CubeSat doesn't necessarily show you flight heritage if you're going to, say, Europa or Enceladus. And
Great equalizer, radiation.
Something that everybody has more control over and more access to is you figure out what the environment is, and you can simulate it here on Earth, and you can show that you can beat TRL-6 without ever having gone to space because you can simulate the whole environment, which is what we do for every flight instrument anyway. And so if you do a mini version of that, It's something you can do without having to go through the whole expensive process of getting there and say, yeah, we're going to have confidence that it's going to make it.
It's true, yeah. Almost anything doesn't have heritage when you go to a place like Europa or Io, where the radiation environment is incredibly intense. So thinking about that and retiring risk in that area can be a good move. So let's take the last question and then we'll wrap it up.
Well, just a comment. I haven't heard anything said about the ISS, which is a way that you can fly something. Oh, you can get TRL. Yeah. It's not exactly in vacuum, but it's also there's a lot of money on the HEOMD side, and they've done biology for decades now on the ISS.
So I did say ISS.
I'm sorry.
That's okay. And we've sent microfluidics and funded stuff for that. We've sent, that's absolutely. Yeah. But thanks, if you didn't hear it and you were hoping, I'm sure no one else heard it. So thank you.
Yeah, so we've said a lot of acronyms. So just to review a couple of them. TMC, so those are the people doing technical reviews of missions and instruments. We talked about P-STARS, so that's the Planetary Science and Technology for analog research. Other acronyms that we threw out. Picasso, that's the low TRL program. And Matisse is the high TRL program. Maturation program. But I just want to go back to the assessment group. So. Oh, TRL, technical readiness level or technology readiness level. One of those. No worries. We got you. Yeah, I just wanted to go back because we're a science community. Let's circle back to this idea. So Jim actually said something, maybe we should have an astrobiology ag. I actually think that we should just raise the noise floor in the existing communities because at this point in time, everybody said, oh, Mars has been very successful. Let's have our own ag and then we'll have 10 missions. That's not how it works. The next mission isn't just owed to anyone. You have to get in and roll up sleeves and accept the beating that will come as you get through the process. And so those assessment groups are really important. And I don't remember when the next MEPAG one is, but the next Outer Planets assessment group meeting is going to be in San Diego in September. And so I would highly encourage folks who are interested in that. If you can't make it to San Diego, it's sometimes hard to get travel dollars to do that. We've been trying to get at least a few early career folks there for each of those meetings, and that will again happen for the September meeting. But they're always online as well. And so listen in and comment and talk on, ask questions and try to participate in that process because it's a long lead time activity. You have to be thinking about it 10 years before it's going to happen. So I hope that's hopefully helpful. Did you have something, Linda? Oh, there you go. SPEC, the Small Bodies Assessment Group. So anyway, I hope this has been at least informational for folks. Please come to those AGs and please talk to your planetary science colleagues, and let's just try to raise the noise floor on life detection and complex chemistry and all these things that we care so deeply about, so that in 10 years we're having the conversation about all of the detections we've made instead of, or maybe it'll be 20 years, instead of how are we going to make this time. So.
And I'd just say that LPI, our sponsors here, the Lunar Planetary Institute, hosts websites for each of the AGs. And so if you just want to get a flavor of what sort of business gets conducted, there are agendas and presentations. So you can take a look at I guess I don't have to. Technology, yes.
Microphone
what
out
is
of my
this?
way so I can
Yeah, exactly. Anyway, so you can look there and get a flavor before you dive in and see what people have been doing. So.
Yep. Well, I'd like to thank our panelists. So if you join me in a round of applause.